Okay, so in this first video we are going to introduce the normal distribution here. So let me start with an example. So let me give you an example of something that is usually considered to be a true normal distribution here. We'll say that the height of adult males is normally distributed with a mean of 69 inches and a standard deviation of 7 inches. Okay, let's see. Zoom in maybe. Yeah, that's pretty good. Okay, now let me show you first of all what I mean by normal here. I'm going to, on another sheet of paper here, if we took all the height of adult men, kind of took a census of all the adult men, and we took all that data and organized it, we could make like a histogram here, right? And along the bottom here you would have like the heights here along the bottom, and this center here, this would be the mean, in this case like 69 inches, and these would be like the frequencies. Okay, and so you would have this distribution. Of course, the majority of people are going to be like average height here in the center, and then as you get shorter and shorter and you get taller and taller, you're going to get less and less people. Okay, and it's going to kind of taper off in the same way in both directions, and it's going to form this symmetrical curve. And if I draw kind of through a curve through these points, then I would get a curve that's shaped like this, and this is the well-known bell-shaped curve that you see on a lot of statistics textbooks. Okay, and there's actually a mathematical equation that would actually give you a curve like this, like you could put it into a graphing calculator, and these tails actually go off in both directions forever. They get infinitely close to this horizontal axis, get closer and closer without ever touching it. Okay, and the height of adult males, of course, there's going to be a shortest person and a tallest person, but this idea of them kind of getting infinitely close is kind of like we're never going to put a cap here. There could always be someone maybe a little bit taller than the tallest person, a little bit shorter than the shortest person. Okay, but it gets so close to that axis here that the area underneath the curve in those tails is pretty much negligible. Okay, so what we're going to do here is we are going to ignore the actual height of the bars, because these frequencies for adult males, these would be in like the millions, right? We're going to ignore the actual data, and we're going to just look at the curve. Okay, so what we will do is we won't have a vertical axis here. We'll just have that horizontal axis that's going to have the heights. Okay, and we're just going to draw this normal curve like this, simplify it. Okay, and we're going to use this symbol. This is the population mean, and then this is the population standard deviation. So when I talk about the height of adult males, I'm talking about the entire population. So these are Greek letters, a lowercase m and a lowercase s in the Greek alphabet, mu and sigma. And so the mean would be in the center, so I'd put mu is equal to 69. Okay, and then the standard deviation I'll put right below it, and that's going to be 7. And now, as it turns out, for all normal distributions have that same shape to it. The scale along the bottom might be different, but they all have this bell shape, and pretty much all of the data is within 3 standard deviations from the mean. So what I can do is I can count off 1, 2, 3, kind of equally divide it there on the top, or to the right of the mean, and to the left of the mean, 1, 2, 3, like that. And then I can actually calculate what these heights would be. So 69 inches plus 7 inches would be 76 inches. I'm just adding 7. If I add 7 to 76, I get 83 inches. If I add 7 again, I get 90 inches. Okay, now I subtract 7. So if I subtract 7 from 69, I get 62 inches. This would be 55 inches. Subtracting 7 again gives me 48 inches. And pretty much all of the data is within 3 standard deviations from the mean. And this actually makes sense because 48 inches, that's actually like 4 feet tall. And that would be pretty short. That would be kind of the short extreme for heights of adult males. And 90 inches is actually 7.5 feet tall. And that's really pretty tall. Okay? So, not that there can't be anybody shorter than that or taller than that, but I would say those are pretty much the outer extremes. Okay? Now, as it turns out, we actually know how much data is within 1 standard deviation from the mean. Okay? And this is for any normal distribution. There is 68% of the data within 1 standard deviation. Okay, so 68% is a little more than 2/3 of the data. So within 1 standard deviation, you already have over 2/3 of the data. Okay, within 2 standard deviations, you actually have 95% of the data. So already pretty much all of the data is within 2 standard deviations. There's only 5% on the outside of that. Okay, and within 3 standard deviations, you have 99.7% of the data. So that is pretty much all of the data. There's only 3/10 of 1% that would lie outside of that, below 3 standard deviations, above 3 standard deviations, this little bit. And so 3/10 of 1% is actually 3 out of 1,000. And I would say that's about right. If I took a sample of 1,000 people, maybe there'd be about 3 people that are either shorter than 4 feet or taller than 7.5 feet. Okay? Now, if you're wondering where do these percentages come from, the answer is you can get them using this table, the standard normal table. And we're going to learn how to use this table in the next video. But what this does is it gives you area underneath the curve. Okay? And for example, like within 1 standard deviation, this is a certain portion of the area. Okay? And if I shade it, that's a certain percentage of all of the area. And the table here, these are the areas in the middle, and they're actually 4-digit decimal numbers. So the area you actually get for this 68% is 6826. And that's a 4-digit decimal number, and if you move the decimal point over, you get 68.26%. Okay, so this is 68% is what it would be rounded to the nearest percentage. Okay? And this 4-digit decimal number can kind of be thought, you can think of that as a probability. Okay? You can think of the area underneath the whole curve as 1. And just like if you add up all the probabilities in a probability distribution, it would equal 1. You could consider this a probability distribution where you randomly select an adult male, right? And you're going to let x equal the height of the adult males. And then these along the bottom, these are like x, we call them x scores. These are the x values. And then if you want to know what's the probability of randomly drawing an adult male between 62 inches and 76 inches, it would be 0.6826. That would be the probability. And that'd be to the nearest percentage, it would be like 68% chance of getting an adult male between those two. Why is that? Because 68% of all adult males are between those two. Okay, so the areas under the curve represent probabilities. Okay, and we're gonna find probabilities instead of getting the total number of adult men and the number of adult men that are, let's say, between 62 and 76, and dividing the two like we did in chapter 4. We're going to look up areas on this table. Okay, and we're going to get it that way. By the way, this table is really handy because the way you find areas underneath the curve, if you've taken calculus in high school, you know that there's a thing called the integral, and the integral is it's a calculus thing, and it actually represents the area underneath the curve. And fortunately, we're not going to do any calculus in this class. We're just going to learn how to use this table. Okay, and so you'll need to stick around for the next video to learn how to use that table. Okay, so there's one more thing we need to look at here, and we're going to use this when we get to the next section, which is going to be finding the probability for, they're going to be application problems for any normal distribution. Okay, so this last thing, see, these are called the x scores. That's what those are called. So corresponding to each x score is a z-score. Okay, and the z-scores here, the center, the mean, is actually 0. Okay, and this is 1, 2, 3 standard deviations above. So 76 would have a z-score of 1, 83 would have a z-score of 2, and 90 would have a z-score of 3. And 62 would have a z-score of -1, 55 would have a z-score of -2, 48 would have a z-score of -3. Okay, so the z-scores go from -3 to 3. Okay, and you can have z-scores that are less than -3 or more than 3, but those are very rare. Most z-scores are between -3 and 3. Okay, and each of these z-scores, like in this case, would correspond to one of the heights. Or I should say one of the heights correspond to a z-score. Okay, and so the point of doing all of this is that every normal distribution has these same percentages underneath it. In fact, one thing I didn't mention earlier is that the empirical rule is actually the rule that says you're going to always get these percentages between 1, 2, and 3 standard deviations. Okay, so these will hold for any normal distribution. So I suppose it's called the empirical rule because they've actually empirically have looked at different populations and saw that those percentages actually hold. Okay, so the percentages are the same for any normal distribution relative to the z-scores. So in other words, any normal distribution, whether it's height of adult males, weight of newborn, or whatever it is, okay, between -1 and 1, between those two z-scores, you'll always get 0.6826, or 68% rounded to the nearest percentage. That's what you'll always get. And so what you do, instead of looking up heights on this table doesn't have any heights, you look up z-scores on the table. Okay? And we're going to look at how to do that in the next video. But what you're going to need to do, though, is you're going to need to be able to take whatever normal distribution you have, you're going to need to be able to convert the x score, whatever it is, to a corresponding z-score. So let me give you an example. Let's say I have an x score here. We'll say it's 57.5. Okay, and that's going to correspond to some z-score down here. And we want to know what is the z-score. It'll be something between -1 and -2. And so the way that we can convert an x-score into a z-score, so we're going to use the following formula. It's called the z-score formula. And we're going to end up using this a lot in Chapter 6. Okay? So the z-score formula is you take whatever x value you want to convert, so it would be the 57.5. You subtract the mean, and you divide that by the standard deviation. And then when you do that, you are going to get the z-score. So let me do the example I have here. So my x is 57.5. My mean is 69, and my standard deviation is 7. So the z-score will be 57.5 minus 69 divided by 7. And you always have the x-score first. Even if this is less than the mean, you're going to put it first, because that's actually how you're going to get a negative z-score. Okay, when you subtract that top, you'll get a negative number. And so now, let's look at how to put this in our calculator. You got to be careful. If I just go to type it in, 57.5 minus 69 divided by 7. So if I put it in like that, what do you think? Will I get the right answer? Okay. If you said no, you would be right. And the reason is because the calculator knows the order of operations. What the calculator is going to do is it's going to do the division before it subtracts. Okay, because it's always division before subtraction. But you actually want it to subtract first. Okay, and then divide. So I either need to put parentheses around the subtraction and then divide that by 7, or the way that I do it is I just do 57.5 and then I subtract 69, hit equals, and that gives me a negative 11.5, and then I divide that by 7. And then I get my z-score. And you're going to always round the z-score to 2 decimal places. And the reason for that is because when you look it up on the table will always have the z-score to 2 decimal places. And so that would be the z-score. And that actually fits here. Right? It's between negative 1 and negative 2. In between there, closer to negative 2. And that's exactly right there. That makes perfect sense. So that is an introduction to the normal distribution, some of the ideas, and also this z-score formula. In the next video, we are going to learn how to use this standard normal table.